Hello everyone, and thanks for joining today's webinar. My name is Vera, and I will be your moderator. Before I hand the mic over to our experts, I have a few things to mention. First of all, we would love to hear from you during today's presentation, so please, if you have any questions, enter those through the Q&A button. These questions will be answered in the end of this session. The webinar will be recorded, and you will receive a copy of it delivered to your email account later after this session. Now, over to our experts.
Hello and welcome everybody to our webinar Machine Learning Meets Embedded Development. My name is Michele Rossi, and today with me, Simon and Amit are going to present together what is our vision regarding a better collaboration for boosting your application when it comes to integrating a machine learning algorithm and a Qt application. First, we want to start highlighting which are the scenarios that we are seeing across the world in general in the embedded space. So today, the current scenario when companies want to deploy an application on different kind of cross-platform use cases are seeing huge complexity already today in terms of collaboration between different departments and different teams. We are seeing UI UX designer, developers, product managers working all together in order to deliver the new product on the market. So what we are seeing today on the market is an additional complexity that is entering in each company, which is the integration of a new expert in the team, which is the data scientist or machine learning expert. But adding competencies and adding new people on the team is also growing the complexity on how organization in the future will have to work together to deliver the product on the field. Some of the pain points that we have been identifying that are relevant across all the industries are faster go-to-market. Of course, when you are delivering a product on the field, on the market, you want to be faster than the competition. You want to be the first to deliver the best-in-class product, right? And especially when you're using Qt, the value it's already there. But when it comes to integrating the additional expert in the team, the complexity will be increasing. And then, of course, the scalability. So you want to deploy your Qt application, including your machine learning model across all the target platform that you're already able to target today. And of course, one of the important pain points that the industry is facing, increasing today, even by the complex scenario that we are seeing on the chip manufacturers, is the OpEx cost. So I want to reduce as much as possible this cost in order to be successful and have more margin with my own device. And that's why we are working with Econo here to provide a way to basically solve the challenges that are highlighted below in the slide. We want to basically provide a unified tool chain that allow machine learning expert, data scientists, UI UX designer, product managers, and embedded developers working all together in order to streamline from a unified tool chain and maintain the product also in the after sales cycle across all the target platform that we are enabling already today. So this will be presented by Simon and Amit in the next phase of the webinar today. But just for you to understand the kind of tool chain that we are envisioning here in order to boost your productivity. But what is the gap that we are looking to solve here? So we are looking basically to close the gap between data scientists and all the other embedded stakeholders, providing a unified chain to speed up the development and deploying your application across all the target platform that you are considering. We want also to help our user and customer today to be more successful with deploying your IP, your expertise, leveraging existing tool chain, right? So in terms of also CapEx cost, avoiding to do yourself your own SDK, to build your own tool chain, that's one of the most important costs that we are also seeing in the market. So how companies today, they are investing a huge amount of time and effort in developing their own tooling, but also maintaining that tooling instead of focusing on their expertise. And that's also the other gap that we want to close. So enabling you to be faster and more productive with an existing and already proven tool chain. Having said that, I will leave now the stage to Simon, that is going to present to you the first step from a machine learning expert, and then Amit will move forward on how the other embedded stakeholder will be able to work closely with the machine learning expert. Stage is yours, Simon.
So, thank you. My name is Simon. I'm a machine learning engineer at Econo Solutions, and I work with supporting our customers with their machine learning applications and helping to come up with new use cases for edge machine learning. Let me share my screen for you. So Ekkono is a Swedish software company. We were founded in 2016, and our main product is the Ekkono software development kit. We have 3 software libraries for doing machine learning on constrained platforms. We have Econo Edge, which is the core library for doing model training and inference, and it's written in C++. We also have another library called Crystal that has a subset of edge features, and it's written in C, and that's the library we use when we run on microcontrollers. And then we also have Econo Primer, which is a workstation version of Econo Edge, where we have more advanced features such as AutoML, feature selection, and general operations for data wrangling. So that's operations that you won't need to run in a deployment scenario, but they're very useful during the development phase. And Primer is also written in C++. And our SDK has extensive tutorials and documentation on our machine learning tools and how to take them to the edge, to embed them in your target platforms. We have bindings to other languages, such as Python, which many machine learning professionals work with, such as myself. And you have a very brief example there of how it looks when you import the 3 libraries into Python. Our API is designed for analyzing streaming time series data. That's where we see most of our industrial use cases. And our models are optimized for incremental training, or incremental learning, as we call it, which is that we're not only supporting models that are trained on a workstation and then deployed on device, they can actually continue training on device, or training specifically to learn a specific behavior that's unique to the device itself. And that unlocks a new array of use cases. So today I will talk a bit about my perspective to this as a machine learning expert. I will talk a bit about how we work with developing and supporting deployment of data-driven solutions, and we will do that by looking at an example use case. In this case, we will monitor the temperature in an electric motor. And some of the key factors of my work is, first of all, the specification of the problem and the solution. So we start off generally with a very broad description, in this case, monitoring of temperature in an electric motor. But we want to drill down. What does that mean? What temperature are we monitoring? Where does it, well, what do we actually want to detect? And what's the expected benefit from knowing that? What data will we need to collect in order to, first of all, develop this solution, but also to verify it? And what is the machine learning model supposed to output, really? Because we can say that we want to do the monitoring of the temperature, but what are we supposed to predict? Are we supposed to output a signal indicating that something has changed? Are we supposed to output a signal predicting the future temperature? Or are we supposed to output a signal that's just an alarm, a binary signal? So specifying what is the expected output of the solution. And once we have that in place, we move on to the data validation stage, where we either collect data or we gather it if it's already been collected before. And we validate that it's enough for the development and evaluation of the use case. And we will also try to look for insights while we're at it, because often the data hasn't been thoroughly analyzed before. So are there any outliers in the data, any anomalies that we need to be aware of? And once we have that in place, we start a process of iterative development, where we iterate on the different computations and machine learning models that come together to form this output that we desire. And we will keep measuring towards our evaluation target, which we, at the end, will try ourselves against. We will test all the scenarios that we can theoretically see that our model might be put in. So I will work here in Econo Studio, the environment that I'm sharing right now. I will give a very brief description of that in a moment. And once I'm done with my part, once I've gone through the specification, some of the data validation, and then talking a bit about the development and evaluation, I will hand over a machine learning model. I will export it from my code here. And then I'll send that over to Admit, and that's something that he can import. And together with my input-output specification, he can design an application around that. So that's the timeline that we want to put together here. So what is Econo Studio? Well, Econo Studio is a workbench for developing edge machine learning solutions. It's hosted here in the browser, and we have put all of our 3 libraries in this Jupyter Lab environment, where I can run these interactive code documents that are good for, well, visualization mostly, and rewriting code in different segments. So moving over to the use case. Well, the very general description that we started with is the monitoring of temperature in an electrical motor. But we'll dive a bit deeper into that. So currently, there is no temperature sensor in this hypothetical scenario in motors that are already out and running in the field. So the idea is that this could perhaps be inferred from indirect measurements. So if we know how much current we're drawing, if we can look at the temperature of the coolant, we can maybe compute what is the actual temperature of the motor. And we're not just interested in measuring the temperature on the outside of the hull of the electrical motor. This is measuring the stator winding temperature. So the hypothetical customer in this case has installed one of these temperature sensors and gathered data on the stator winding while the motor is in operation. And from these, I see 2 use cases that go into each other. The first one is that we want to use machine learning for replacement of a physical sensor with the virtual one. And that would be applicable to all of these motors that are already in deployment, because a virtual sensor will rely on the other measurements that are available to infer this value. And once we have that virtual sensor in place, we can very quickly build a predictive alarming use case around it by, well, in the first stage, we can add a threshold to it. So whenever the prediction surpasses 90 degrees, that means that the motor is running too hot, and we can issue a warning to the user. But that can be further expanding by adding, for example, confidence intervals to the predictions, which is something called conformal predictions that we have in our library as well. So the data we'll be working with, these are sensitive measurements that are done using a temperature sensor. Data can be used in different ways. There's some data required for the development. So in this case, we would need at least one example, one time series of the motor running with the installed temperature sensor. It would, of course, be great if we could add more of them. Either the motors can be running in a different environment, so we can compare the qualitative differences between them, or maybe even another type of motor or a different size of motor, just to see if the learnings generalize across them. And then for deployment, we will need to know which are the sensors we actually put into the solution and at what rate, what's the sampling frequency. And that will be determined, that will be an outcome of the development process. And then the goal is to arrive at this virtual sensor that will take in motor signals and output the predicted stator winding temperature. And we will do that conceptually here, and then we will transfer that to Amit, and he can replicate that in Qt Design Studio. So this will be a replacement for the physical sensor, and then we can reach the predictive alarming use case by adding the threshold. So moving on to the data validation, we load the data sets that we have been granted, and the data on a very high level looks like this. So these are all the signals in the data set, and we can see the label for them up here to the right. So the first one is the ambient temperature, and then we have the coolant temperature. We have two voltages, we have the motor speed, we have two currents, and then we have the stator winding temperature. So that's the one we want to predict. So in a real scenario, we will only have access to the first 7, and we want to create a machine learning model to predict the 8th. And now we can verify that we have that, and we can see that we have a lot of variation as well. For example, we can see the RPM is going up and down all over the place, meaning that we have a lot of actuation in it. We have a lot of use of the motor. The data set would not have been suited if we were just idling all the time. So we consider that this is good enough to create the first prototype. And what we also do during our data validation phase is that we look at, well, what are correlations between signals? Are there any relationships that we can use? Do we see that the stator winding is directly correlated to something that we already measure? And well, in this case, it seems to be correlated to, well, the coolant, for example. So that's information that a model can use. But we see that it's not very clear, it's not very linear, which means that we will have a good position to try a non-linear model, like a neural network. And once that is done, we have confirmed that this data is good enough for development and then deployment. We move on to the development stage. And we can do a bunch of different things here. One of the things we allow our models to have is an integrated signal processing pipeline. So we will just give the model the unprocessed signals, and we can tell it to define operations on it. And in this case, we add some moving averages to them. So we add filtering, basically low pass filtering of the signals. And then we feed those to the model as well. So it will get the raw signals and the low pass filtered signals. So that in a way will tell it how to process the information. We also consider how we want to evaluate the solution. And in this case, we have one data set with one time series, and we split that up into different sections. So here we will take 60% for training, and then we'll take 20% for the testing, to verifying that our solution can actually generalize and predict the temperature on data that the model haven't seen before. And we do this to make sure that the model doesn't overfit, doesn't just memorize the relationships straight away. We want something that's general. And we try around different models, and in this case, we end up with a neural network where we have 3, 5, and then 3 hidden nodes in it. So it's a 2-layer neural network. It's very small. The model totals at 2.2, 2.1. kilobytes. So it's a very small model, this one. But the idea is that during the development phase, you start trying out these different configurations, different model types, you iterate upon it to arrive at the best one. And then for the evaluation, we can measure errors of the model. So in this case, we have the mean absolute error, which is what is the prediction error on average. In this case, it's 4.2 degrees. And if we plot them, we can see that they're quite closely aligned. The dark green one is the real stage rewinding temperature, and the light green one is the prediction. And they're very close to each other. We still see some locations where we miss, but most of them are dips actually, which we're not that interested in because they're not representative. Well, they're not included in the overheating. But of course, if we could add more signals to the model, or perhaps refine it further, we could find an explanation for these as well. But as it stands, this model is good enough to try out in this proof of concept stage. So once the model is trained, I can just save it. So I've now saved it from Python, and I can send this model over to Emit, and he can import it either into the C++ library, or he could take it directly into the Qt Design Studio using the Ekkono and Qt plugin, which he will do in this case. So over to you, Emit.
Hello again. First, I would like to discuss the traditional design development workflow. Designers share graphical assets and images as Photoshop and animation as text document to give more precise idea of what is needed. But the developer builds the user interface from the scratch by checking the graphical assets and the text document provided by the designer. Until development is not finished, design validation is not done. Each new change in the design will add workload on the developers. Late validation of the design in development cycle and shift of responsibility of design validation to developers are real issues. These issues are due to the limitation of the tool, because tools are not collaborative. They are not common between the developers and designer. Non-collaborative tools make it more difficult to achieve satisfactory graphical quality, and it's often the source of the tension between the teams. Qt is already solving these pain points by enhanced UI development workflow. Qt created Qt bridges on the four main design tools: Photoshop, Figma, Sketch, and soon on XD. These bridges allow to export the work of the designer to the Qt Design Studio. Import of the artwork is pixel perfect. Once designs are in the Qt Design Studio, designers can add animations and effects directly inside the Qt Design Studio. And once the UI is validated by the designer on the final target, the same design work can be given to the developer, and developer, instead of creating the UI design, they work on the backend connection of the UI. The difference between us and the other tools is import and animations are interpreted in the QML language. This is the QML language between the design and the development world. Once UI is validated by the designer, the same QML document then given to the developer, and developer is now adding the C++ or any other backend connection to the QML language instead of creating the UI from the scratch. Responsibility of the UI design is now only to the designer. Developer, they spend their time doing the backend connection and of course, then deploying it to the real target. In this workflow, no need to wait for the full deployment of the application on the device. Preview of the design can done directly by the Qt Design Studio. Once we enable the designer developer to work in the enhanced UI workflow, we realize there are more to do in this workflow. One part we are exploring with our partner Econo. Thanks to the Econo integration in the Qt Design Studio and the Qt Creator, now both designer and developer can also work in the machine learning models. Goal is to ease the integration of the machine learning with the UI, test machine learning algorithm and UI together. Machine learning engineer work on the Econo Studio and generates the target machine learning model. UI designer work inside the very popular design tools, and this design is then imported inside the Qt Design Studio. Once both design and model, machine learning model is imported to the Qt Design Studio, connection of the signal to the machine learning model is done by dragging and dropping as any other graphical widget. Once input and output of the machine learning algorithms are made, Design Studio enable interaction engineer to test with the machine learning model directly on the real hardware target. Once the UI along with the machine learning models are tested by the interaction engineer, the project can then pass to the developer. In this workflow, the machine learning algorithms are also validated during the design process. I will present an application. A UI design is done inside the Photoshop. Machine learning model is generated in the Econo Studio. My dear colleague Simon, he has already generated a machine learning model for a electrical motor. I will use that model in my demonstration. I will import both UI and the machine learning model inside the Qt Design Studio. I will quickly add some simple animation to the rotor of the motor. Then I will show how to make integration of the electrical machine learning model generated by the Simon. I will add some dummy data file. I will use dummy data file for the input of the machine learning and display some predicted value which is being generated by the machine model. I will first run my UI project and machine learning model on the Windows PC. And finally, when I'm happy with the output of the UI and the machine learning algorithm, I will deploy the same project from the Design Studio to a Raspberry Pi. So now I will show you this demonstration. So let's first see the Photoshop artwork of this UI design. So here I'm opening the Photoshop. This is the UI of this motor. The goal of this UI is to predict the stator temperature, which is calculated by the machine learning. So I have created a simple UI in the Photoshop. On the right hand side, this particular component is developed by the Qt. It is called Qt Bridge. This allows your Photoshop artwork to import inside the Qt Design Studio. First, you have to provide a path where you want to export your design work and simply click on this magic button, export. I have already exported this artwork. I won't do it again. This is the Qt Design Studio, a tool for the designer and the interaction engineer. Here I will import the Photoshop artwork which just I exported. So let's first create a new project, a empty project. Let's call it motor. I can give it the screen resolution. This I can change later as well. It will create just an empty project. So first thing first, what I have to do is the import my assets. So this is just empty project with a form widget which has just a text document inside. So first I'm going to import my artwork. So I have exported in the ML. This is the Photoshop export. I'm looking of a metadata file. This file contains all the information of the Photoshop document, Photoshop artwork, which I was showing you before. And during this this import, the Qt Design Studio will create the reusable QML component. It will also import all graphical images and place them in the right order. So now if I see my project, there is this motor board UI component which is already created. And if I open this QML, this is the UI which I just imported from the artwork. And this UI is the pixel fiddle from the Photoshop. So you can see this is the Photoshop document, and here is the artwork inside the Qt Design Studio. So first thing first, let's add the animation in the rotor movement. And for that, let's go inside this motor component. This is the motor component. So I would like to rotate this internal part. So if I switch off, so I would like to rotate this image. And for that, I need to create a timeline. So let's create a timeline for this. So a timeline. I click on the plus. I will create a timeline animation. I will have 360 frames in this timeline, and let's give a duration of 5 seconds. This timeline, it will be a continuous timeline animation, and I just close. So as soon as I do that, I have this new timeline created. So now in this timeline 0 to 360, I will add some rotation on this rotative image. So I go to the advance, and on the 0th frame I add the rotation to 0 degree, and then I go to 359, and here I add rotation to 360 degree, and on 360 I add a rotation of 0 degree. So a complete rotation is done. So if I go now, so I have a rotation. So I save this, I go back to my top level, and here if I go to my top level component, which was created by the default, I was showing you this is the empty UI. I need to remove this, and now as I was importing the artwork, so those artworks are creating the libraries. So I can just include a new library, and as soon as I include my library, you can see that there are new components available. So I can just drag and drop this component in the top layer UI. I say this component is filling all my UI. And now I'm running this project. So it went to other screen. So if I bring it back here, so you can see the simple UI animation is already created. Now it's time to integrate the machine learning algorithm. And for that, I need to copy the machine learning algorithm which created by the Simon. So I have the machine learning algorithm here. Along with that, I have some static data. So I copy those algorithms and I put in my motor project. So I copy them directly here. Once that done, I go back to my machine learning. I'm going to add those machine learning model inside my project. So I go inside my component, motherboard component, and here I'm going to add those machine learning model which is created by the Simon. But for QML libraries, add a library for reading the CSV file where my data is there. I add the Econo components, then I add the electrical motor components. And now if I go into the QML components, you can see I have extra graphical widget to play with. So I will put these graphical components in my QML file. I start first with a predictive QML component. And in this component, I have already added the machine learning model itself. Let me show you the source code. So I am taking the model from this file. Now I'm going to add some input attributes to this model. So you see I have a large set of library. So I will use attributes. So I put attributes in this. And then one by one, I'm going to add the input attributes to this machine learning model. So my first attribute, it's called ambient. It's the ambient temperature. And the data of this ambient temperature is coming from my data feed, which is my CSV file, from which I'm taking all my dummy data. So I'm binding ambient with this. I put some extra. I don't need this one, so ambient. Then I put another one. This one will call coolant, and its value will be data feed dot coolant. Then I put another input attribute. If you remember your electrical courses, so this is the voltage field. So it will be data feed dot ud. So D component, and then I have to put a V component, Q component. So the input is coming from the data feed dot u underscore q. Okay, and then I have to put the speed. So all these parameters which I'm giving here are the parameter are the input parameter of the model, and the prediction is the output temperature as the stator temperature, as Simon was telling before. time is I_t. Okay, so and the another current component is I_q. It is coming from data feed dot I_. Okay, and then the last one is the time attribute. So this one is let's say timestamp, and this one is coming from the data feed dot time in millisecond. Okay, so I have put all input parameters, and now let's put the predicted temperature, which is being predicted by the model itself. So it's here. So I can go here, and actually this is also a set pointing. So 44 is not the constant value. Instead of that, I want Econo dot predicted Econo those predicted value. So this one will be predicted by the machine learning algorithm, and then I want to just have let's say 1 decimal point of it. So I save, and now I'm ready to run. So for running, it's quite easy. You just press your run button. It went to other screen. Let's bring it here. So right now I have just put the prediction temperature, but I have another project where I have binded all of them. I'm going to show you that as well. So here is my other project, and this one I have binded all the input to the UI. Let me run this one. So here you can see the whole UI is reacting based on the input parameters. So the prediction temperature from the machine learning algorithm is very, very similar to the what we were measuring by a real sensor. So you can see the model is really nice. So you don't always have the sensors on the motor where you can measure the temperature. Sometimes when you have the actual sensor, you can measure that, but most of the time when you don't have the sensor, you need to calculate this the temperature of the mesh of the rotor itself, and here that is done by the machine learning algorithm, and then based on that temperature, maybe you want to raise an alert, or maybe you want to increase the coolant flow to the machine itself. So this is a prediction done for a particular kind of scenario, so temperature in this case. And now when we are happy with the UI and the machine learning output, this project can be then deploy. I can select my Raspberry Pi and I can deploy it to Raspberry Pi. So let me show you first my Raspberry Pi. So here is my Raspberry Pi, and it is running a Linux called Qt from the Qt company. So it has several examples. It is already connected by the internet and with my Qt Design Studio. So I'm going to just select a new kit. I was deploying before for the Windows. Now I'm deploying for the Raspberry Pi here, and I will just click and it will be deployed. So yeah, it is being deployed. So that's it. Now the model is deployed to the Raspberry Pi. You can see it is reacting same way as it was reacting on the Windows PC, and my whole UI is reacting on the base of the input and of course the output, which is the predicted temperature of the stator. So now if you want to try all these tools, feel free to contact us. You can reach out to a local Qt contact, or you can reach out to our local Econo contact. You can write us a message on this URL. So it's time for the question and answer. So if you have any questions, it's right time to ask. We will all reply your questions.
Great. Then we have another question. Can you please suggest any hardware where machine learning with Qt examples are available?
Maybe
Maybe
Amit?
I can
Yeah.
take that. Yeah. So those Qt machine learning algorithm, as well as the Linux, which my Raspberry Pi was running, we are compiling from the source code. So if you have a customized board, ask us. We can provide tools in the source code format, and then you can cross compile everything for your particular hardware. Otherwise, we have few already pre-built Linux image and machine learning algorithm library. For example, we have for the Raspberry Pi, IMX6, IMX8, and XP boards are already there. So there are some pre-built tools available. And if you don't find your hardware in this pre-built list, then we can provide everything in the source code format so that you can do the last step, that is compiling libraries for your customized board. I hope that answers the question. Thank you.
Yeah, Amit, there is one question. Which IMX6? If you have like,
yeah, so we have the IMX6 ULL and CAD core from the Toradex. We are also working with the IMX6 from the NXP, so NXP development board. So those are all already supported. And if you want to look more information, which boards are supported, you can go to our website in the device creation section, and there is all listed hardware already, all supported hardware already listed there. And there are already few IMX6, as I said, from the Toradex and XP. I think there is one from the boundary device as well.
Great. The next question, what machine learning use cases are good to get started with?
So I can take that one. So very similarly to the example that we just showed you, we recommend that you stay focused on the available signals and start defining a machine learning use case from them, at least for the first one. And then you can build the complexity on top of that afterwards. So in this case, we started with a simple temperature prediction, but then we can add more layers to it over time. We can create this predictive alarming use case. And of course, if we were to go to predict into the future as well, could make it, well, even more predictive in that case. We typically see that you focus on what possible inputs do we have. When we think about a specific component, maybe we're monitoring a valve, for example. So in that case, you want to measure both the valve actuations and then at least one signal that's related to that, for example, pressure. So we can learn with machine learning algorithm what's the normal behavior. And then we can detect as those start to drift over time.
Okay, and the following maybe question for that, I'm wondering how much data is needed to do machine learning?
Well, of course, that depends. We see that machine learning is typically done in two different ways. The first one, you take a very quantitative approach. You gather a lot of representative data. For this case, it could be that you gather data for all different motor sizes that you're interested in predicting for. And the second one is having a more qualitative approach. For the quantity approach, you would collect, for example, maybe 15 time series of normal runs, and then maybe a couple ones where it's faulty. And then you train an algorithm on a very high level to recognize those and classify them. But we also see a more qualitative approach where we look into the data in fine detail. We maybe just have 1 or 2 examples. And then we see inside of it that, for this case, the cooling might be very important for predicting the state of winding health. And then it turns out that we can actually learn what's normal for each individual engine. This is what we call incremental learning with Ekkono. So in that case, you take a pre-trained model, you deploy it, and then you continue training, learning what's normal on that device. So for those cases, you don't need that much machine learning. So it all depends on which approach you take to it, which of course will be reflected by the use case that you have.
Thank you, Simon. And then I guess this goes for Amit. What all machine learning examples are available for IMX6?
Yeah, here as well, Rajesh, the machine learning algorithms, even our tools, we are not bound to a particular hardware. So everything is available in the source code format. So if you are looking for a particular ML example, you can create out of the Ekkono and Qt tools. But if you are just wanted to test the example, the motor example, which me and Simon was showing, that is already an example available. But our idea is not to bind ourselves to a particular hardware device. Rather, we provide a generic solution by which you can deploy the machine learning algorithm to across almost all embedded devices.
Thank you, Amit. I have a couple more questions here. I have my own model pre-trained. Can I use that with this tool chain?
So I can answer that. Let's see here. So the short answer to that would be that we don't support it this day. So we have our own models that we support loading of in our library. We are looking into support for like generic architecture such as ONX into the future.
Thank you, Simon. And then there's one from where you got the Raspberry Pi Linux image on which you were deploying machine learning and UI application.
Yeah, maybe I can take that. So one good thing about the Qt ecosystem is Qt is already integrated with the embedded Linux build system, like you might know Yocto and the build root. So you can build your own Linux image for your development boards by using build root and Yocto. We are already present there. But if you are looking some pre-built Linux, for that, as I was telling before that we already provide some pre-built Linux for a large set of development board. So whether you build it by the source code or whether we provide this pre-built Linux to you. I was using Qt pre-built image on the Raspberry Pi, and this pre-built image is called boot to Qt. And those, these images are there. These pre-built Linux images are there to accelerate your development without much worrying about the BSP layer. So in my example, I was using a pre-built Linux for the Raspberry Pi, which was compiled by the Qt company.
Thank you, Amit. Okay, I think there's one more question. How do I test the Qt application? Its framework is supporting tools for testing purpose.
Maybe that one I also can take. So the Qt framework has Qt test module for the simple testing scenarios. And for the extended scenarios like checking sequence of the screen, QObject status can be tested by the fog logic tools like Coco or Squish. FogLogic is the part of the Qt company. For that, you can also contact us. We can provide you both Qt tools and the FogLogic testing tools.
Okay, thank you, Amit. I think we are now running out of time, but I would like to thank Amit, Simon, and Michael for joining and for the great presentation. And like I mentioned, this webinar will be recorded and you will receive a copy for it delivered to your email account after the session. Okay, I can see there's one more question from Sebastian. Oh no, that was only a comment. Right. But yeah, thank you all for joining. And if you have any more questions, please contact us on info@qt.io. Have a great day.